Okay, thank you very much. I'm Roberto, and this is the work with Luigi and Marco. So let's start. Okay, so what is the main motivation? So let's start from entanglement theory. In entanglement theory, there are some quantities. For example, here is the relative entropy of entanglement, which is the minimization over the set of separable states of the relative entropy, or some further quantity, which is the geometric measure of entanglement, which is just the maximum fidelity between your state and the set of separable states. And these quantities were widely studied in entanglement theory. And they studied this because they have some very nice properties, and they can extend. They can be extended for any resource theory, for a wide class of resource theories at least. And one of the main questions is, what about the resource theory of magic? So what about if we replace just the set of separable states into the set of stabilizer states? And this question probably hasn't been studied that much, and especially some properties, which I define later, which are called additivity properties, they haven't been yet well understood. So we try to make a little bit of progress towards that. And yeah, what we really cared about was the mathematical framework of this, because in this sense we could develop some technique to recast the original convex optimization problem to linear ones, so that they could be solved. So I will go through there later. So okay, what is the resource theory of magic? Probably I don't need to explain it, but we can just think of them as applying some threefold circuit, which is composed by Hadamard, phase gates, or C0 to the zeros, and then we get pure stabilizer states, and to get the whole set of mixed stabilizer states, we just take convex combination. And the whole idea is that a Clipper circuit is efficiently classically simulable. So the idea of magic is to inject some magic state and give some kind of quantumness, so that it is not efficiently classically simulable. And in this sense, this can be seen as a quantum resource. Okay, here just to briefly introduce. To give a more concrete picture of what are stabilizer states, in the qubit case, this is the block sphere. These are all the axes, and the eigenvalue of the Pauli operators are pure stabilizer states, and then from out of there you take the convex combination and you build the stabilizer octahedron, and outside of there are the magic states. And here on the symmetry axis of the octahedron, I will specify a bit later. There are these T state and F states that are states that have some nice symmetries. Okay. What about magic monotones? So as I introduced before, we looked at this relative entropy of magic, that is just like relative entropy of entanglement, but just minimized over the set of separable states. And the other quantity we really looked into that is stabilizer fidelity. And as we will see later, these two quantities, they have very different properties, additivity properties. And why do we care about that? Because first of all, they are monotone under any set of pre-operations. So this is a very strong requirement, a very strong monotonicity requirement. This includes also non-physical operations. For example, like this morning, like this non-entangling operation in entanglement theory, that is the biggest set in OCC. And anyway, also in resource theory of magic, this satisfies a very strong monotonicity assumption. And this is because of the underlying property of these divergences called data processing. Then they have some very nice properties on convexity. So they are convex. Well, the fidelity is truncate, but anyway. So under mixing and strong monotonicity properties. So monotonicity on average. So these are very nice properties that are shared by a wide class of resource theories. So what can we say about this? So first, the additivity question here, I just state it clearly. We have two states. R is a monotone, is additive. R of rho 1 times rho 2 is just the sum of R rho 1 and R rho 2. This is what we have by additivity and the tensor product. And what are the application of this? Well, if you have system composed of many qubits, then you can just compute the magic, for example, numerically, of each of the single qubits and then sum up the quantities and get the magic of the total system. And this is kind of doable, but the point is that if you try to just compute the magic of the whole system, since it can grow very big, this might not be a simple task. So in this way, we can just compute more efficiently the magic of multiple copies, and other implication involve tasks that involve many copies. So for example, distillation, or anyway, also technical reasons. For example, when you calculate these regularized quantities, it means you don't need regularization for these quantities. Okay, let's go into the main technical results. So the first one is about the stabilizer fidelity, and then we can show that it is multiplicative for all single qubit states. So here is rho I is a set of single qubit state. Then we have f of the tensor product is equal to the product of the f. So in this case, I say multiplicative and additive. I just mean log fidelity would be additive, but fidelity is multiplicative. So I use them interchangeably. And so the other nice thing, we also give a closed form for stabilizer fidelity for all single qubit states. So this quantity is really nice. And as long as I know, there are not many closed forms, even for single qubit states, at least for divergent, for monotones based on relative entropies, the research of magic. The other closed form that we could get was also for what is called generalized robustness of magic, that I will briefly talk later. And so it's really nice. So it's multiplicative and closed form. And okay, what about relative entropy of magic? Well, sadly, relative entropy of magic is not additive, and someone can just come up with a counterexample. So here is a counterexample. But however, if we have a set of single qubit state, and they are special, kind of. So if we call tau I the optimizer, so the closest stabilizer state to the state y, if it commutes with the input state, then for all but one, so if you have two, you just require one commuting, then it becomes additive. And so some examples are the one I described before. For example, this states located on the symmetry axis of the octaedron. So this T, H, F states. So relative entropy. So for example, Mount's rates for summations, but it's not that nice. Okay. The second case is for specific multi-qubit states. So what I mean by specific, here I try to draw it. So we have this state rho, and rho is in between a pure state psi and the fully mixed state. And we also require that the optimizer is in this line. So is in this line that intersects a pure state with a fully mixed state. And this is sometimes not the case, but for many states considered in literature, that have some symmetry, this is true. So what we can say, so here I call it the polarizing channel, just mixture of pure rho, 1 plus 1 minus p with a fully mixed state. Then this is in a more complicated way what I was trying to say before. So we have at most 3 qubits, and I will say why. So rho I is the polarized of pure state. Also, the optimizer is the polarized of the rho, which is on the same line with the pure state. Then, in this case, we have both the fidelity is multiplicative and the relative entropy is additive. So some examples are Toffoli, Hogger, CS, the polarized states. So one open question that we could try to solve and that we still have is that I showed you before that fidelity has nicer additivity properties on the tensor product. We couldn't prove that for all 2 and 3 qubit states, for example, the fidelity is multiplicative, but only for this set. And we expect that this to be true. And but for the relative entropy, no. Relative entropy won't be accurate. Okay. So we have two monotones, fidelity and relative entropy, and then like what about generalized robustness or anything you can come up with? And so we try to give a bit of a big picture. And how do we do this? We introduce, we call them for me. Alpha Z any relative entropies. They depend on two parameters, alpha and Z, and you can just minimize them, and you get some monotones. And how does the whole parameter space look like? So here we have alpha and Z, and here we have 1 half and 1 half, the stabilizer fidelity, so minus log fidelity, and alpha equal to 1 is the relative entropy line. And then, for example, well, okay, you usually think of Dmax. For some of you that are familiar with this divergence, that's the limit alpha to infinity, alpha of the sandwich, but you can also see it as a limit of this alpha Z, not in this line, but in this line. So that you have to prove. And then what you also have to prove is that the monotone built out of the Dmax, which is the generalized robustness, is also on this line. So there are some technical points there where you have to prove like monotonicity along this line and able to some interchange some limits, but that we could do. And what happens is that we can identify two classes of monotones. One that are in this red line, that are located at the boundary of this blue region, which is the region where they satisfy data processing. And these monotones on this boundary, they are additive, they are fidelity-like. So they satisfy stronger additivity properties. So we can show that for all these monotones on these lines, the same result as for the fidelity they hold. And in particular, also for the generalized robust magic, which you can see as a limit. And for the inner region, the blue region, these are not going to be additive, and they are like relative entropy-like, so they satisfy weaker additivity properties. So if you want an additive quantity, my suggestion is either look at generalized robustness or fidelity, and you will have more chances. Okay, one main idea of the proof. Yeah, so we wanna, the original optimization problem is a bit hard. So, well, if you take powers of convex combination, they don't behave well on the powers. So what you can look, and later I will explain why, it's this quantity, F0, which is the maximum overlap of a state rho and a stabilized state phi. And then you can prove multiplicativity of this. So if you take a tensor product for y, then you just get the product of this f of 0 for y. And the way we do, we use a trick, and a very simple trick, and we use the results on multiplicativity for pure states. So why this weird quantity is that additivity problem doesn't, for mixed state, it looks more complicated than pure state, because these quantities are not linear. For example, the fidelity for pure states is linear, so everything is simpler. But actually, we can see that we can recast the original problem into a linear one. And how do we do that? We had some previous work on entanglement theory. So yeah, the whole idea of the project was to kind of use of the state-of-the-art techniques in entanglement theory to show additivity, to try to do something in resource theory of magic. And what we have is that we have a quantum state in some alpha Z in this data processing range. Then the optimizer satisfies some linear condition. So trace of sigma is f by f, I mean free state, so it's stabilized state. of this guy that I won't define, but this some positive operators must be more than this Q alpha, which is the exponent of the D alpha I define here. So as you can see, this trace sigma chi is linear in sigma. So if you, in particular, if you maximize over sigma, you will just have the maximization over the Q state. And if you recall that zero, this is exactly that zero. So in particular, if you have this chi that is multiplicative on the on tensor product, what you can do, you just get your as your optimizer, the tensor product, this optimizer of the marginal problems. You just plug it in, then you use it is factorizes. You just plug it in, you maximize, you use the additivity, the multiplicativity of that zero, and then you get something, and then you use that each of the optimizer was the optimizer of the marginal problem to satisfy the whole composite condition. It's a bit, hope you can follow, but this is more or less the idea. Is the main idea is to just look at this at zero, which is very simple. And so does this happen? This chi factorized on tensor product? Well, for the fidelity, yes. For the max relative entropy, I mean, in the limit for this whole line, and then we use the limit result. It happens, but for the relative entropy, you can see that this gradient, this chi would be the gradient in the end, doesn't factorize. It is like one. This kind of points out why they're not additive. Okay, thanks.
All right, any questions?
Thank you for your talk. I have two questions. One is that you say that magic state is not stabilized. Does that mean every magic state plus the Clifford gate is universal?
Yes.
Oh, and then my next question is, what does more magic mean? Because you have a quantity. If the magic is larger, does that mean it can allow you to produce more T gates while the non-Clifford gates?
So, so the point is, well, I don't know. Like the word magic is not very like maybe appreciated by all the community, but historically it's called magic, and the whole idea is that you can build these gadgets made of Clifford, and then you can input a magic state, and then you can realize a non-Clifford gate. So in this way, you can achieve universal computation.
Yes. Maybe my question will be, what is the physical operational meaning of the measure of your magic?
So my measure quantified. So you have many magic states, and you want to say how much magic is that? Give me a number.
Yeah.
My measure would be a number. And if you have two states, how does this behave? For example, yeah, that's
okay,
it's very similar to entanglement theory.
Yeah, can talk more. Any more questions?
The way you the additivity that you mentioned is for tensor product of single qubit states, right? What happens if like the tensor product of an arbitrary 2 qubit state and let's say a 3 qubit state, whatever?
Okay. So for let's say 3 qubit states, any 3 qubit state, I expect that monotones on the boundaries of the data processing region will be additive. We don't have a proof for all states, but for some classes of states, eventually, if you consider very multi-qubit, multi-qubit states like qubit states, yeah, it won't be additive. So so you need to consider like up to some like single qubit states, 2, 3 qubit states, and probably that's the most you can do.
Questions? Is a question? Ah, no.
Hi, thanks. Is it possible to recover the results about multiplicativity for 1 qubit mixed states using Ullmann's theorem and the multiplicativity for 2 qubit pure states?
So I haven't thought about Ullmann's theorem, but we wanted to do something that doesn't involve the stabilizer fidelity. But it's just a very simple proof for example, for generalized robustness, or just looking at all of them without using any specific properties of the monotones to just derive a general statement. So probably for fidelity, there might be some specific techniques that they also work.
Questions? So in one of your pages, so you gave a counterexample of additivity property using a single state.
Yes.
And so the additivity violation can be small. So is there a maximal violation result of that? For example, when the dimension is high, it behaves like log D.
Yeah, I haven't looked into that.
Okay, so you have one example and the additivity fails.
Yes, you can find an example. I was more interested into when additivity holds. That makes sense.
Okay, we still have time, so any more questions? Yeah, I have a question. So you have defined these generalized measures with different alpha and c. So I wonder, is there a meaning? Let's say I pick a certain alpha and c compared to another one. Can I say something what this means in terms of the resource theory or the operational meaning?
So it really depends. So some of them they just pop out from tasks. So for example, if you have this dyadic simulators, you would get the generalized robustness as a quantifier out of there. So I don't know of any operational interpretation of any of the points on the alpha Z diagram, but some of them they have. So for example, generalized robustness. It's just a way to just say, I just have one monotone and I just want to study one monotone, and then I just vary the parameters. So I could include most of them.
More questions? No? Let's thank the speaker again.